Okay, this is a video about light, and before I start I just want to point out a few things about the relativistic slide rule. One thing is it always gives a right angle here. In other words, this is always Brewster's angle. In other words, Brewster's angle plus the angle of transmission. If you add them together, you always get 90 degrees. So this is the angle of incidence, and the angle of reflection is the same as the angle of incidence. And that also means that the light heading off in the reflected angle is always S-polarized. Slapping, that means S-polarized. Okay, and the frequency doesn't change because, say this is an antenna. See, my pen's moving up and down at a certain speed. That's not going to change. Now let's say it's hitting this thing at a certain speed and then it slows down. So the frequency hasn't changed, but the wavelength has dropped because the velocity's dropped. So the wavelength drops with the velocity, and this is the phase velocity here. So as I was saying, this is the angle of transmission, this is the angle of incidence and reflection. Add them together, you get 90 degrees. So I just want to point all that out. Okay, let's go back to the slide rule. Okay, so let's test it. So choosing a B value of 0.6, which means a phase velocity of 0.75, which means we're talking about water, so into water. So notice here that I'm changing my phase velocity. Well, this is not the phase velocity, but I'm changing the velocity, and notice the frequency is not changing. It's just C over M. So here, okay, and now I'll just put this on. So here it is, and see that's 1.333. So that's the refractive index of water. This is the phase velocity, and I'll show that the intensity of the transmitted slapping waves is 0.48 times 2 squared. Okay, which you can see there, the 0.48. That's the distance from there to there. Yeah. Did we get it? Yep. I don't know. Distance. Oh, come on. To there. From there. Okay. Now let's check it out. So first of all, colors. I've just chosen 450 nanometers, which is visible light. So on the electromagnetic spectrum, anything with a wavelength between 380 and 700 nanometers will be visible, and then I've divided by 2 pi, so in radians instead of radians. Yeah, so here's the frequency, W. Here's the K value, radians per meter. Here's the frequency in meters, so it's 2 pi times m. That's the wavelength. See, it's dropped. It's only 0.75 of the 4.5. It's now only 3.375, which is 4.5 times 0.75. And you multiply wavelength times frequency, you get the velocity. So there's the velocity. Make that one, because it's 0.75 c. Okay, so that's colours. Now, what about the refractive index here? Okay, this is the angle, 53.1. If you can look on the model, you'll see here on the it's 53.1, and then you see the angle of transmission is 36.8, and you'll see the intensity is 92.16%, and the velocity through water is 0.75 c, which is the phase velocity. So just make sure all that's correct. Now here's the intensity. As I was saying, it's 2 times that length squared, or 4 times the linear inertia. Take your pick. L squared over T is by dimensional analysis, it's the Weber, which is magnetic flux. And you can see that's the normal way of calculating it, and that's how I calculate it with the slide rule. That'll be the amount of reflected light, because it wasn't transmitted. It's either reflected or transmitted, and that's polarized 100% with the slide rule, because it's always Brewster's angle, the angle of incidence. Critical angle, and here's that 36.8 degrees for the transmitted angle. Here's the angle of incidence, 53.1 degrees. Okay, I think that's everything.